Hello everybody and welcome. I want to just make a quick remark on continuity. Somehow I forgot to mention this in my big continuity video that I did. So the point is that if you haven't seen the first continuity video, please watch it before you see this one, because I'm assuming in this video that you've already watched that one. So as I highlighted in the previous video about continuity, a continuous function is one where you don't have to lift your writing utensil as you're sketching the function, the graph of the function. And so what this means is the following, that the left-hand limit and the right-hand limit are going to be the same. And for continuity to be upheld, this is going to have to be equal to f of a. Okay? And I want to talk about this for a moment. Let's remember that this condition by itself, this is the condition for a limit to exist. Okay, if the left and right hand limits are the same, then the limit exists and it's equal to whatever that number is that you're approaching. And it's possible to have a limit exist but still not be continuous, and we've highlighted this already. If you have any type of hole like this, then as we're sketching, if I sketch, when I get here I have to lift my utensil, come over here, and then sketch some more. So this, this is a discontinuity. It forces me to lift my utensil when I'm sketching. Discontinuity. And if this were filled in, then that means, okay, so look, check this out. Here's the limit. The limit is the idea of getting closer and closer and closer to this point from both sides. And then if I fill this thing in, now there's no longer a discontinuity after I fill it in. So after filling, we are continuous. Okay, and so this point would be the x equal a, y equal f of a. That would be this point. Okay, so that is the situation there. If you want to be continuous at any point, then this must be the case at any point in question in order for your function to be continuous. Okay, now this is a little more useful than you might think, because let's turn this thing around a little bit. If you know the function is continuous, I'm going to write this down, this is important. So here we go. If you know f is continuous, over an interval containing x equal little a, then the limit, the value of the limit, is equal to f of a. And this is where a lot of confusion comes from, because for any continuous function, the limit will be equal to the function value. And so what will happen frequently is the student will take this a little too far, and the student will always think that all you have to do is do f of a to find the limit. And that's only true if you know for certain that the function is continuous. Okay? And so so continuous functions, right? Continuous functions. Let's write those down. Any polynomial. Okay. Any polynomial is continuous. An example of a polynomial is, f of x equals 3 plus 5x minus 10x squared plus x cubed minus x to the fourth plus 0.01 x to the 10th. This is an example of a polynomial. So some number times x to any power. You can have any number of terms that you want in there. It's still a polynomial. Polynomials are continuous. The exponential functions are continuous. Okay, exponentials are continuous. So we're talking about, e to the 3x, that's exponential, minus 2 to the x, plus 3 to the power 5x. All of these are exponentials, and all of these are continuous from negative infinity to infinity. Minus 10 to the pi x. Okay, these are all exponentials. All these are continuous from negative infinity to infinity. What else? We got the sine function. Also the cosine function. Both of these are continuous everywhere. Okay. Okay, now let's get into some functions that are continuous over their domain but have a restricted domain, right? So R for reciprocal, 1 over x, right? So the domain of this function is everything except 0. Okay, so it is continuous on its domain. Continuous on the domain. But remember, the domain does not contain 0. Infinite discontinuity. I'm kind of abbreviating here. Infinite discontinuity at x equals 0. Because that gives us division by 0. And we don't want that. Okay. The same is true for any power of x, right? 1 over x squared, 1 over x cubed. They all have the same property. Anytime there's a function of x in the denominator, you want to make sure that you exclude those numbers that give division by 0 from the domain. Okay, so tangent is continuous over its domain, but what's its domain, right? So tangent is the sine over the cosine. And so if cosine x equals 0, because that's the bottom, if the denominator is 0, then the tangent is undefined. Okay, and so what angles have a cosine of 0? Well, it's going to be 90 degrees and 270 degrees. And in radians, that's just pi over 2 and 3 pi over 2. Okay, but remember, these are periodic functions. They go forever, right? So it's going to be x cannot equal pi over 2 plus any multiple of 2 pi. And then x cannot equal 3 pi over 2 plus any multiple of 2 pi. And realize that if you take pi over 2 and add pi, you get 3 pi over 2. So these can be combined in the following way. X cannot equal pi over 2 plus any multiple of pi, not 2 pi. Because if you add pi to 3 pi over, or if you add pi to pi over 2, you get to 3 pi over 2. And then if you add pi again, you're back to 5 pi over 2, which is the same thing as pi over 2 as far as angles are concerned. Okay, so as long as x is none of these, then your tangent is continuous. But these values are not part of the domain, right? So the domain, I have to use set notation for its domain. It's going to be the set of all x such that x is not pi over 2 plus pi k, where k is any integer and x is any real number. Okay. So these are the things that we have to keep in mind when we're talking about continuity. Whether something's continuous at a point or not. Are there any, you always have to, basically you have to find the domain. You have to find the domain, and whatever the restricted values are, that's where your discontinuities are. Otherwise, your function's going to be continuous. And then, like I said, these up here are continuous truly everywhere. One last little example here, right, is the natural log. I guess we'll do 2 examples. And then the square root function, right? So if we remember the exponential, not the logarithm, but remember the exponential. The exponential, the y value of the exponential, the y value of the exponential has to be bigger than 0, not bigger than or equal to. This exponential curve will never touch 0. The y is bigger than 0, and x can be anything, right? X can be anything from negative infinity to infinity. The logarithm is the inverse of the exponential. So swap out the x and y. In other words, for the logarithm, x is greater than 0. So the domain of the logarithm is parentheses 0 to infinity for that reason. And here, this one's very, very similar, except 0 is okay. What's the square root of 0? 0 times 0 is 0. So the domain here is going to be x greater than or equal to 0, or bracket 0 to infinity. All right. Good. So yeah, so these are the things that we got to think about. If we have a logarithm, whatever the number is inside the logarithm has to be bigger than 0. If we have a square root, remember we can't take the square root of a negative number because it's not real. And then other functions, just make sure that the denominator can't be 0 because that gives us division by 0. And this is really all we have to think about is there a logarithm? It's got to be bigger than 0. Are there any even roots? It's got to be 0 or bigger. And then is there any opportunity for division by 0? Otherwise, everything is continuous always, if none of those things apply. All right, so that's going to be it for this video.